Good evening, everybody. My name is Janelle Laros. I am from Kailua Kona, Hawaii, and I'm a member of the class of 2017. My entire life, I have always been fascinated by science, but absolutely horrible at math. But regardless, growing up, I always participated in my school science fair, and when I was a sophomore in high school, I was looking to fill another science credit, so I signed up for robotics. Now, when I first walked in, I immediately felt out of place because the class consisted of a clique of senior basketball boys just trying to get the credit, a group of genius computer kids who had already spent years coding, and a whopping total of 2 other girls in the class who also were incredibly brilliant. But regardless of how out of place I felt, after a week of being in the class, I realized that I love robotics. I love being able to use my hands to create, design, and build something which then comes alive. I loved it so much that I wanted to continue robotics in a more complex and challenging program, and I then did a year-long independent science research course to pursue robotics during my junior year, and I then continued it into my senior year, which brings us to where we are today, where I am building a multi-jointed robot controlled by specific biosignals. So, with this project, I was given the space to learn how to code, build, and design in a self-led and non-traditional classroom setting. I was able to re-inspire my love for science, which contributed to my furthering my interests in my other classes, as well as academically challenging myself in science. Finally, this project has allowed me to redefine my self-identity as someone who cannot be stopped by their weaknesses. So what is a multi-jointed robot controlled by specific biosignals? So my goal was to build a 4-legged robot that had a hip and a knee joint at each leg, and that would be controlled by biosignals. Biosignals are any signal that are in living beings that can be continually monitored or measured. The three biosignals that I was using was EMG, electromyography, which is the electricity of your muscles, ECG, electrocardiography, which is your heart rate, and EEG, electroencephalography, which are your brain waves. EMG, your muscles, would control the initial joint movement of the robot. ECG, your heart rate, would control the speed of the robot, and EEG, your brain waves, would control the direction of the robot. And as you can see, this is a diagram of the most recent prototype that I've built. This is the 3rd one, and this is all of the labels. As you can see, the foot and the knee and the hip joint, the Arduino, which is the brain of the robot, and several different battery packs and a breadboard. So I first started this project by learning more about biosignals. I was able to learn about biosignals through a company called Backyard Brains, which creates basically Arduino-compatible biosignal equipment. The first ones that I was studying was EMG and ECG. This led me to design my first prototype, which I made out of Legos. What made this prototype unique is that I created the tendons basically out of string and elastic, which was then connected to a fixed point on the robot. This is an animation of the first prototype. And now this is an animation of it trying to walk. Creating a walking robot is harder than I thought it was going to be. The tendons, basically, they couldn't support the weight of the chassis, and the Legos also broke under tension. This led me to create my second prototype. The second prototype, instead of the string being connected to a fixed point on the chassis, it was connected to a servo. And if you don't know what a servo is, basically, let's say you have a motor, which is a continuous rotation, and if you have a servo, then you can put like specific degrees, and that's where the servo turns. So this had a servo which was adjusting the tension in the rope. This was a lot more of a more successful method, but at the same time, since it was built out of metal, it did not break like the Legos did, but it was not able to support its own body weight. So this led me to the summer between my junior and senior year and the first semester of my senior year. I took time to research. The 3 parts that I researched is first, I took the time to further my knowledge in coding, specifically the code language of C++, which is the language that Arduino uses. I also took this time to research other multi-jointed robots, such as Big Dog by Boston Dynamics, as well as other 3D printable multi-jointed robots that I could study their joint movement and see how I could apply that to my project. In this time, I also was able to learn how to use AutoCAD, which is an online computer-aided design program, which is similar to CAD, which is another kind of program that most engineers use. I did this so I could design my project before going into the third prototype. Then this leads us to where we are today. This is the third and final prototype that I've built. Instead of having tendons with rubber bands and string, I actually just made another servo to be the knee. Here is an animation of it being able to pick itself back up. I know. And here, this is a video. This is a progression of my robot over the past 2 years. So this was at the end of my sophomore year when I first got the idea for it. This was the first design that you saw earlier. This is the first prototype. As you can see, there were many struggles along the way. And this is the most recent prototype. And now this is the most recent video we have of it walking. Now you see every servo movement is a specific degree that we had to input into the code. And you can see as the code re-loops, it stands itself back up. So each of these are specific angles. And that's about it. So, as you know, I am graduating, and my influence on this project is coming to an end. But next year, oh man. Next year, I have 2 rising juniors, Jackie Payne and Haley Emmons, who will be taking over this project. Both young ladies have advanced knowledge in physics, coding, and robotics, and I know that they'll be able to continue the project in ways that I couldn't. So now, why is this important? Especially because, as you saw in the presentation, I did not finish it. I did not integrate the biosignals into the robot. But I know that with Jackie and Haley continuing it, they will be able to hit the ground running and implement biosignals into the project. But over the course of the past 2 years, I was able to study and research all of the biosignals in isolation. I made 3 different prototypes. I taught myself a CAD program and furthered my knowledge in C++ and Python. I studied biomechanics and movement, which I then applied to my project. This project also allowed me to win my school's 2016 Engineering Award, as well as being selected as one of the statewide winners for the National Center for Women and Information Technology's Aspiration in Computing Award. Now, if you told 15-year-old me, who was intimidated by an elective robotics class, that I'd one day be recognized for engineering and computing, I would not have believed you. But recently, I also realized that it isn't about the recognition, that this project is about its legacy. The other day, a freshman actually came up to me and she said that the reason that she wanted to pursue independent science was because of a presentation I gave about this robot over a year ago. And that's when I realized that this impact extends past me. So to anybody who needs to hear it, know that it's not our inabilities that define us, but it's how we overcome them. And it doesn't matter if you think you can't do something. If you are passionate about a subject and are willing to be motivated and put in work, anything is possible. Even for a girl who's bad at math but wants to build robots. Thank you.